Okay, confirm clear. All right, so I'm on the second board now. I'll continue with what I was saying before about functions. So basically, I just said a few things about why functions are important. And functions have rules that map between sets, right? Given two sets, right? A function maps between them. I'll define this a little bit more carefully in a bit, but I'm going to talk a bit about sets. Actually, I'm not. I'm going to cheat and not talk about sets, but I'll try and talk about subsets of affine space. And so in the same time, I'll set up some notation. So yeah, so this is not going to be anything about set theory. I'm staying well away from that. So I'm gonna, for this course, I'm gonna let K be a field. And if you don't know what a field is, don't worry. We can assume that we're looking at real numbers, complex numbers, or the rational numbers. I don't know why I wrote them in that order, but most of the time we'll be working over the reals or the complexes in this class. So if you've dealt with real numbers and complex numbers, you know what a field is, and we're all good. But I'll refer to a field as just K. So what I'll define here is Kn first, which is just going to be, I think, at the n tuples, right? So you've got n numbers, and each of these numbers are coming from K, all right? So n-dimensional vector space. But of course, right, this is a vector space, and often in algebraic geometry, we are not interested, or we don't want to emphasize the vector space structure of Kn. So we'll actually call this, we'll actually call this An. And K, right? So it's actually the same thing. I'll just say Kn with, without the vector space structure. And all the varieties that we'll be defining, studying, are going to be varieties inside some n-dimensional space over K, inside some A and K, which this is called the affine n space. Maybe I shouldn't say equal there. It's just called. Oh, I can't do that. Called affine n space. I guess over K. Now, sometimes, the underlying field K will be understood, and we'll actually want to refer to the coordinates of this in kind of a notation. So this is something I learned from my advisor. So we'll write like this, we'll write if we want to or need to label the coordinates. Need to label the coordinates. So yeah, here I'm just saying that the first component, the first coordinate is called x1, second is called x2, all the way up to xn. So all of the subsets we'll be dealing with are going to be subsets of An. So we won't talk about sets, but we will talk about subsets of An. So to define a subset of A and K, what do? We have this little notation that Dan introduced last week. We have some curly brackets. We specify, some point in A, and then we specify some condition that these points have to satisfy, these these n tuples have to satisfy for it to be in the subset or not, right? So we provide I guess I'm going to call it a decision procedure to decide whether X is in, I guess, X or not. So I can define a subset X of this, right? So we've seen examples like this before. I'm going to move on to the next board. Just write some of these down. Right, so examples are, let me see. Yeah, so examples are going to be, varieties. Right, this is kind of what we talked about last week. I think this is the V that you used, and maybe like f, we'll just use a single f, right? So this is going to be some a inside a and k, right? Given that f of a is equal to 0. So this is another piece of notation that I'm going to write down here. There's going to be a lot of times where we talk about a point A inside affine n space, but we won't need to write down all of its components, right? So I'll simply just write A in A and K, and then I'm going to apply the function f, some polynomial f to it, evaluated at A to be 0, right? That's the condition you check to determine whether A is in the subset VF or not. And so this is a nice shorthand because often, we don't want to write this all the time. I know the book does this, and but I think it's good to be able to read both, right? As you can see, these two lines contain essentially the same information. We just have to remember that A has multiple kind of components. So that's an example of a subset of A and K. We can also, the other thing that we won't study in this class, but we probably will see, semi-algebraic sets. All right, so instead of having equalities here, we change them to inequalities. So examples going to be like this, right? So I will write this down in this case, and I guess I'll also write like this. And so something like this. Oh, maybe not x, maybe y. Y squared less than or equal to 1, right? So this is your standard unit disk in on the number plane, and so this is also a subset of A2R in this case. And so other examples, right, you can have things like the singular locus of a variety. So I'm sneaking this in here, not because it's especially important for this class, but I think one of the aims of running this class was to talk a little bit about singularities. I'm not sure whether we'll actually get to it in the mag proper, so I'll mention it here. The singular locus of varieties is actually itself a variety. It's defined by, I won't write this out now, I'll just say it. It's defined by the vanishing of some minors of a certain Jacobian matrix that you can construct from the defining equations of x. So those equations that you get are, again, polynomials, right? So this is itself a variety because it's defined by a bunch of polynomial equations. And so we also have like complements of subsets of A and K, subsets. Well, I mean, these are all subsets, so I won't say are subsets. And you can also take unions and intersections, right? So maybe I should just say complements, unions, intersections. Okay, so these are, probably going to cover all of the subsets that we'll be interested in. Now, when we talk about monomials and Dixon's lemma and things like that, we're going to be talking about subsets of like monomials and the lattices. So those things are countable or finite, so I'm going to leave them. Hopefully finite sets are simple enough that we can pretend that we understand them. So I see we have a question there in the chat. Why is a semi-algebraic set called a semi-algebraic set? The semi refer to the lesson. Yeah, I guess yes. Right. I actually don't know exactly why it's called a semi-algebraic set, but yeah, it's because of the inequality that they call semi-algebraic. Okay, so I'm going to move along here. Hopefully, I was able to catch that third board. So now I'm on the fourth board, and I can talk a bit about functions. So functions. Okay, so given subsets x and y of a and k and a and k, so given subsets x of a and k and y of a and k, And most of the time in this class, actually, this second dimension m there is going to be 1. We're going to be looking at functions, polynomial functions on n's with n variables, or polynomial functions in affine n space. It's just going to map to a number, right? And so those are the functions that we know and love. And so m is going to be 1 most of the time. So a function is a rule. Well, I should probably name it and give notation, right? We'll write it like this: f(x to y) is a rule which assigns which I should say for each x in x. So maybe this is notation that Dan's already used last time, but x in x means that x is the element of x. Hopefully this is not news to you. X in x, such that, what was I saying? Yeah, it's assigning an element for each x in x, an element y, which will write fx in y. And in fact, it's going to be a unique element, right? There's only one value for each value of x. And for every x, this function is defined, right? So there's no elements of x such that you can't evaluate f on. F has a value on every element of x. And so some notation and terminology, x is called the domain of x. Sorry, f, not x. And the y is called the codomain of f. And I'll put this in here because I think it'll come up. This is called the range. We'll denote it fx. And this is going to be points f of x for every x in x. And this is called the range of x. Or sometimes also image of x, f. Sorry, I keep saying x instead of f. These are all properties of the function, so of f. So yeah, so we'll talk about these things at some point. Now, which board should I hop over to? Maybe over there. Do I have to disconnect from the org to walk? I can walk, right? Okay, let's just all go over to the other 4 boards over there. Okay, cool. Thanks for erasing the boards. And more notation. Okay, maybe I should wait until everybody's here first. So more notation, right? You often see this. More notation, right? We'll often write down the function like this, and we'll put x, small x, with a little arrow with a vertical line there to fx to indicate that this is a rule that maps x to f of x. And sometimes we'll also write, sometimes we'll just write the usual way, fx equals, I guess y, right? Okay. Oh yeah, I was gonna say that my capital X's don't look like capital X's. Yeah, sorry. Small x. I don't know if this is helpful. Hopefully the context makes it clear. So we say that f is injective. So this is the usual thing that we go through. Hopefully, I'll be able to give some interesting examples of injective, bijective, surjective functions. Injective, if f small x is equal to f, I wrote down y there, that's probably bad. I'll write x1 and x2, because use the same letter to refer to the same space, right? It's confusing to say small x and small y are elements of x, and then you have a big y there. If implies x1 equals x2. Equivalently, if x1 is different from x2, then f of x1 is not f of x2. Right, so it just means that different things map to different things. Surjective, if for every y in y, there exists x in x, such that f of x is equal to y. So everything in y gets hit, that's surjective. Equivalently, f of x is equal to the codomain of f, which is y. And bijective, if injective and surjective. Okay, so I'm going to give some examples, and I'm going to ask you guys to tell me whether you think these are injective, surjective, bijective. Okay, so the first one, I'm going to write the function like this. Example 1, f of, just a very simple function mapping c to c, and I'm mapping x to x squared. Okay, so can you guys tell me whether it is injective, surjective, or bijective?
Well, it should be neither, right? Or none of them? Because,
yeah.
Because, well, it's not injective because you can have two inputs that map to the same output, like 1 and negative
Very
1,
good.
and it's not surjective because you don't hit negative numbers in the output.
It's from C, so y I squared is the -1.
Oh, I missed that.
I think it's surjective, like you can, if you look at some, the vectorial representation, like how you call that, of complex numbers, then you can shrink by the square root and take half the angle, and you get something whose square is going to be your number.
Cool. Yeah. Thanks. I think both of you are right. The function is not injective because of the reason that was. I actually didn't see who said it because it's very hard for me to see who's talking. It's not injective because, f of 1 is equal to 1 and f of -1 is also equal to 1. All right, so that breaks the rule. But it is surjective. Because I'm just going to say because complex numbers, right? You can always take square roots. Okay, so the second example, I'm going to change the domain and codomain, same function. And so is this function surjective or injective or not or neither? And I think probably one of you already answered this question. Injectivity is the same, but it's not surjective because negative numbers don't get hit. Right now we've restricted everything to real numbers, right? So this is not surjective. You can't take square roots of negative numbers because negative numbers don't have square roots. Very good. So used up a lot of board space, but this is great. I'm gonna eat up all the boards. I'm gonna go to the next one, and I got two more. The next one is, or maybe three more. So the next one, example 3, I'm going to go from here, right? And I'm going to map x, y, z to... I'm messing up my own notation. I'm also not following my own prescription to use affine space, but whatever. We are going to write this sometimes. Okay, so we're going to have this guy here. So again, same questions, right? Yeah, have a think about it and see what you reckon. So if it helps, you can kind of just look at the variable x, right? Y and z don't really do anything, right? Yeah, it's mapping to R3. Yeah. Ah, sorry. No. Yeah, you're right. I should have did it. Thanks. I forgot to. I had it. Yeah. Definitely not injective. It's not injective because I just stuck those zeros in there. Now let's change this a little bit. Actually, let's change this to y and x. Right? Maybe that's what I forgot to write down. Y and z. What about now? Yeah, I don't know. Maybe it's because my notes are crap and I. Nah, no reason. Stupidity. There you go. I think I was getting too close to the middle of the board. Maybe that's why I wanted to save some space on the right-hand side. Yeah, injective and surjective. All right. Any other votes? Yeah, so I think this is fine. You guys are correct. This is injective and surjective, because really is the only thing that's happening is on the first component. You know, it's really the identity map on y and z, so you can really forget about it. That's just really to throw you off. But yeah, x plus x cubed is an increasing function, so it's going to be. I guess, bijective. So second last example, the reason why I messed up in my notes, I had this, I was just gonna write x, y, z. That's really what I should have written here, right? Now we're mapping to R, same function, and I think given that I wrote this down earlier, someone already answered it. This is actually not injective, but I think it's surjective, right? For the same reasons that the other function in example 3 is surjective. Okay, so one last example. This is a fun one. We're gonna look at this. And now we're mapping from C2 to C2, and I'm gonna map x, y to x plus y cubed and y minus x plus y cubed. Okay, so a somewhat complicated looking map from, C2 to C2. So yeah, same questions. Feel free to take a guess if you can't, if you don't know just by staring at it. I, of course, stole this from somewhere, so that's how I know the answer. If I was asked to do this just by staring at it, I would have a little bit of trouble. So Dan, what do you reckon? Yeah, it looks a bit like conjugates. So I got vote for not surjective. Did Dan say something and I didn't hear it? Oh, sorry. No worries. Yeah, so I think for a map like this, it can be difficult to tell whether it's injective, surjective, or neither or both or one or the other, right? I'll tell you what the answer is. This is somewhat of a trick question. I wanted to kind of bring this up to I make a passing remark at something. So this is actually an example I stole from some notes on the Jacobian conjecture. And so the Jacobian conjecture, I'll tell you what this is in a minute. This thing, okay, so the answer is that this thing actually is bijective, right? So this is bijective. And in fact, the inverse of f, right, is given by x minus x plus y cubed, y plus x plus y cubed. And if you compute the Jacobian of this thing, and the Jacobian of this f here is going to be dx f1. I guess this is f1, and this is f2. The dx is partial derivative with respect to x, dx f2, dy f1, dy f2. You actually find that this is equal to 1. Okay, so the Jacobian conjecture says that you have a map between polynomial map, right, where... Oh, shit, yes, sorry. Yeah. Yes, determinant is 1. Thanks, Dan. Right, so what was I saying? I was saying, yeah, so the Jacobian conjecture says that if you have a map like this, you constructed the determinant of this Jacobian determinant, and it's a constant that's not 0, then the map has a polynomial inverse, right? You can write down an inverse function where the components are also polynomial. So this is also, I mentioned this to answer a question that Dan asked me last week. How do you get rich doing algebraic geometry? Prove this, and you might not be rich, but you'll be famous. But don't do it, because it's very hard.
So that's your answer to getting rich is you can't, but you might be famous. All right.
I mean, if you get famous, I don't know if people maybe prove the Jacobian conjecture. Would people pay you to speak? Maybe,
Yeah,
right?
you can get a gig opening banks or something.
I don't know. I mean, if you prove this, you'd probably be pretty okay, doing pretty okay. You'd probably get a job at Harvard or something.
Just to be clear, the matrix being invertible gives you that it's bijective, and then you're making some additional comment beyond that, right? I mean, just having the matrix be invertible only gives you that it's sort of locally bijective, right? So it's not sort of sufficient to give bijectivity.
Right.
Just
yeah. So you can
Jacobian.
get. Yeah. So it's not enough to just say that it's invertible. Cool. Thanks, Dan. So this is like the inverse function theorem from calculus, right? But the Jacobian conjecture is saying a little bit more profound than that. That the whole map is globally invertible if you just compute this determinant, and then you can get it. Okay, so I'm gonna give you some fun examples of things that aren't functions that may look like functions. Okay, so these aren't functions. Maybe they may look like functions. I'm going to write them like this. My pen stopped working. Last digit of x. So, okay, so here's the thing that you might be able to do. You take a real number, you write out the decimal expansion, you try and take the last digit of x and you return it. All right, so this is not going to work because if you ever look at real numbers that you didn't write down, the digits are just random things, right? But even if you look at rational numbers, sometimes you can't even do that, right? You know, you got repeating decimals, there's no such thing as a last digit. So I guess I'm writing this down to say that, you know, functions are fine. We're only going to look at polynomial functions. You can write down a lot of things that look like they might work, but they're not going to work, right? So, you know, another example would be, you know, functions should also be deterministic, right? If you do something like this, you know, R, A, B, you know, if you want, this is a function that you often write like in Python, right? But it's not a mathematical function. But you know, I've certainly written functions like this. I'm going to sample from some distribution, right? Depending on A and B. And so, yeah, this is a perfectly good function that you can write in Python, but it's not a mathematical function because you don't always get the same result all the time, right? You're sampling, you know, sample one thing, I guess, from this normal distribution, you get some non-deterministic thing. Okay, so functions are deterministic. You can write down formulas for them, and so most of the time we're going to be looking at polynomial functions. I've given you a bunch of ways to think about polynomial functions, injective, surjective, and whatnot. We're not going to be looking so much at maps between high dimensional things, but you know, these examples show you that maps between, I guess, maps between these high dimensional spaces, R3, C2, you know, if you can write them down in the algebraic, you should be able to write them down with where the components are also polynomial functions. So the polynomial functions are building blocks for maps between even higher dimensional geometrical objects. I don't want to say, I guess variety, I can say variety, right? And so they're not just, you know, polynomials that you study. You know, you can do a lot more with functions. And so, but you know, for the rest of this class, we'll be looking at mainly polynomial functions of several variables and trying to understand how they can be used to study the variety that they define. Okay, so I think, you know, this is a fun interlude on functions. The last thing I wanted to cover today is mathematical induction. And this is a proof technique that's used a few times in the book because there are some algorithms that will present that calculate some stuff. And since this is a math class, we want to prove that these algorithms do what we say they do. So, you know, there are algorithms to compute these Grabner bases that we'll introduce later on, and there are algorithms to divide polynomials with each other. So when we write down an algorithm, right? We need to provide a proof of correctness, and induction is a great tool for doing this. So I'm going to move over there and give an example of how we can do this for an algorithm you may have seen before. So I'm seeing if the orb will move if I just kind of Cool. Oh, so before I get started on the last part of today, any questions about sets and functions, comments? All right. So let me hop over this board and do some induction. So mathematical induction. So this is a method of proof. I'm just going to write down kind of what I said before. All right, to prove that a sequence of statements, right? And so the sequence of statements are going to be like P0, P1, P2, and so on, right? Indexed with natural numbers to Pn are true for all n. Right, so these statements are, depend on a parameter n, integers, and so there are two steps, right? So there are two steps to this. That's a terrible two steps. Right, so you have a base case, a base step. So you have to establish the base cases. The base case. Sometimes base cases, so P0, P1, all the way up to however many you need to do, but this n is fixed, right? This is fixed. Usually 0 or 1, right? Usually you only have to check a small number of base cases, right? So you can just do this by hand. And depending on the problem, the base case is very easy, is obvious. In a lot of these algorithms that we'll be looking at, the base cases are obvious, right? One of them, there'll be a bunch of variables with certain values. You have to check a condition on them that they satisfy some formula. Usually there'll be a bunch of zeros, so the base case, right, in the first step of the iteration, a lot of these algorithms are iterative, will be very easy to check. So usually it's just one thing you got to check, verifying some formula. And then you have the induction step. Induction. And this is where you assume, my handwriting is deteriorating. So this is where you assume Pn is true and use this to prove Pn plus 1. Sometimes you actually will assume more than that, so maybe I should actually write this down. Maybe I should write a more general version of this because my example actually uses a slightly more general version. I'm going to assume that pk is true for all k less than or equal to n. Right, so for all these statements up to and including n, I assume that they're all true, given that I'm going to use the power that this gives me to show that the next statement is also true. So once the base cases is established and this induction step is established, then automatically we have that all of the statements are true for n. And so next board. Right, so we'll use induction to prove the correctness of algorithms in MAG. And this is a little bit different from how we usually think about induction, right? In mathematics, usually you're trying to prove the truth of potentially infinite number of statements, but algorithms terminate, right? And so we're not trying to prove that an infinite number of statements are true, but we also don't know whether we don't usually have a bound on the number of steps that an algorithm has to take before they get to a result. I mean, we often have asymptotic bounds, right? But given any input, there'll be a bound. But if you increase the input size, the algorithm usually takes that many more steps. And so we don't have a fixed end where we have to prove out. We can't go through and just check the algorithm through by hand for every step. We have to use a tool like induction to prove that once we get to step n, the next step is also going to give you the right result. And so if it terminates at any step after that, or at any step at all, the result that comes out is going to be correct. Now, another thing I'll say here that I won't write down, I'll write down later, is that for algorithms, we have to also prove that they terminate, right? Induction is not enough to prove that they're correct. You can have, you can have an algorithm that is correct at every step, but if it never gives you a result, right, then you can't say that it's correct, right? So there's also termination that we have to prove often with correctness of algorithms. Okay, so I'll kind of write down some of what I said. So usually, usually the correctness, right, is usually stated in a form as the output or outputs satisfying certain conditions. I'll say condition star. And the output variables will have intermediate values at each iteration of the algorithm. Intermediate values. Each step or each iteration of the algorithm. And so here, just very roughly, without being specific about this, the base case P0, right, will be that the initial values of the output variables. So these are going to be variables that are going to be outputted that they have you initialize them to be some numbers at the beginning. They gradually change to be closer and closer to the output. So the initial values of the output variables satisfy condition star. And as I said, if you've written computer programs before, right, when you initialize values, most of them are going to be 0. Some of them are not, obviously, and so it's very easy to check, right? P0 is just basically saying, of course, I look at this, it satisfies the formula or the conditions that I need this to satisfy. Okay, so Pn, right? So the induction step is going to be showing that. We assume that the output variables satisfy star at nth iteration, right? So this is like Pn, and then we use this to prove P star. Pn plus 1 also satisfy star. So yeah, this is usually an algebraic step, right? You take the formulas that you get for the n step, and then you kind of do some algebraic manipulation with them, and then you get the next step. So so got a question here. After n steps, the algorithm is idempotent. Probably not sure if this is the right word, right? So the algorithm usually terminates, right, at some point. And if you apply the algorithm, if you just like call the function on that input, yeah, the same thing should come back. Is this always the case for these algorithms? Yeah, I guess yeah, because no if the conditions are, well, not the conditions start, but the conditions for doing computations. Usually these algorithms, they'll be, you feed some input in, it'll check a bunch of stuff. If it doesn't satisfy a constraint, it'll do some computation and change them. And then once it reaches a point where the kind of conditions for doing more computations are satisfied, no more computations will be done. So I guess in that sense, if you applied that algorithm to an input that already satisfies the thing, it will be unimportant. But is this always the case? Yeah, I'll say yes, and someone can contradict me if I'm wrong. Okay, so let's move over here to the third board, and I'll give an example of something that you may or may not have seen before. I'm sure some of you have seen this before. I'm only going to be kind of hand wavy about this. You can get kind of technical with these things. So I'm going to use an example to prove that. I'm going to prove that merge sort is correct. Okay, so this has nothing to do with algebraic geometry. This has nothing to do with Grabner basis. This is just an algorithm that you may have seen in a standard computer science class. And it's used to sort an array or a list, right? And I'll tell you what to do with the algorithm, give an example, and then prove that this actually gives you, well, what the algorithm is supposed to do is to sort an array, right? So what happens? Usually when you have a list like this, like 3, 5, 1, 2, 7, right? A lot of the times in I guess computer science, you're interested in sorting this list. So you want to return something like 1, 2, 3, 5, 7. Now, how do you do that, right? Now, merge sort is one such algorithm that you can take an array, I'll just say integers for now, of any length, and then swap the elements in some way, and then give you a list or an array. I keep interchanging these two. That has the same elements, but in ascending order, right? So what merge sort does is that it breaks the list into two. So this is an example of how merge sort does it, right? So it will break the list into two. So you break it into 3, 5. Maybe what I'll do is I'll draw it like this, right? So the first thing we'll do is break the list into 2, and then recursively apply merge sort on each of these lists, right? I haven't told you what it actually does, but there are two things, right? So there's a step where if you're given two arrays that's already sorted, there's a way to merge them together to get a sorted list, and you can apply this. So I'll just give an example of how this works, and I'll write down the algorithm. Maybe that's the best way to do it. So we're gonna iteratively divide up, right, this thing, right? So what I'm doing here is that I'm calling the algorithm the first time, and it's breaking up the list into 2, and then for each of the blocks kind of blocked out in red, I'm calling merge sort again, and that breaks the list into 2, and I guess I've done it inconsistently here. I should actually do it like this, right? It breaks it into 2, and then it will keep going. Now, obviously, if you have a singleton list, then sorting it is very easy. You just return it. And here, the third step, you break this into 2. Okay, so now you've got all these lists broken up, and so what we're going to do is we're actually going to merge them, right? So at this step, you've got 2 and 7, right? I'm going to merge these two. So the result of calling merge sort on 2 and 7, you're going to get the same thing back, because 2 and 7 is already in order. And so and then I look at 2 and 7 is already sorted. So then I look at this and I merge them. This is fine. This gives me 1, 2, 7. And here 3 and 5 is all. So I haven't actually done anything, right? 3, 5, 1, 2, 7, they're all sorted. And so the last step is to look at these two and merge them together And so here, 3, 5 is a sorted list, 1, 2, 7 is a sorted list. So so all I have to do is kind of go through these two and merge them together to give you 1, 2, 3, 5, and 7. So maybe this wasn't the best example because I didn't do anything until the last step, until I've gone back up to the first layer. But that's essentially how it works, right? You just keep breaking the list up, keep...
Wait. You're saying you didn't do anything,
Sorry,
but
my
it's
computer
not
went
sorted at the end. So what is the algorithm actually?
Did I do this wrong? Wait,
Your list is not
sorry,
sorted.
did I watch your question?
Well, how do you get
1,
the
2...
output on the right-hand side? I don't follow the algorithm you're outputting.
Oh, okay. Oh, right. So basically, there's a step that I kind of glossed over, right? So when I draw these circles, right, what I'm doing is I'm merging the two sorted subarrays into a big sorted array. And so when you look at here, 2 and 7, well, you don't have to do much, right? 2 and 7 is already in ascending order. 1, 2, 7 is already in ascending order. 3 and 5 you don't have to do. So basically, the only thing that we actually have to do some work on is 3 and 5, right? So you're given 3, 5, 1, 2, 7. I guess you go along, you have a counter that goes along each of these lists, and then you just pop them into the resulting list once you see a number that's greater than the other. That's probably not the best way to say it. So you go along 1, and you go along 2, and you go along 3. All right. Yeah, thanks.
Yeah, okay, I follow. So in the last step where you're merging 3, 5, and 1, 2, 7, but apart from that, nothing happened.
Yep, that's correct. Yeah, I should have written down an example where something actually does happen before then, but the only computation, thanks for adding the ON as well, right? So this is merging the two sorted lists is meant to be quick, right? So because they're already independently sorted, you just have to kind of jump around the two lists to put them together. And so, so this is an algorithm, I guess I haven't told you what the algorithm is. I've given an example. I'll write down the algorithm and then we'll prove that it's correct. And we have a bit of time, so we can spend some time on this, right? So merge sort.
Sorry to interrupt, Kenneth, but given we're going to have to switch to the other set of boards, maybe you want to do the algorithm over on the other set back where we started.
Good idea. Okay, let's walk back. Okay, cool. Thanks. Yeah, so I just saw a comment there. I guess you're right. The induction for this example is not going to be the end step, right? Because it's recursive, it's not iterative, and it's going to be about the size of the input. So when so I was looking for an example to do here. I thought this was a simple enough one. I didn't want to actually intrude into the course material and actually do one of the algorithms to improve it. But I guess this is not going to be exactly like I wrote down before for like an iterative algorithm, and it's going to be an induction on the size of the array. You're right about that. Okay, so all right, so hopefully everyone's back. I guess all the footsteps have stopped, and so a merge sort. Okay, so the first step is to divide, right? Divide. So we're going to divide an array into of n elements. Into two arrays of n on 2 elements each. Now, of course, when I say n on 2, this is not exactly right, because n might be odd, but we can figure out a convention to, divide it up in a good way. But the point is that it's a partition of the array. Nothing is left behind. Okay, so conquer. Right, so you sort the smaller arrays recursively, right? Like using, like this means using cause 2 merge sort, right? It doesn't mean to sort them like by hand, right? You recursively use the same algorithm to sort. That means you go back up top and you divide the resulting arrays into 2 smaller arrays of n on 4 elements, and you keep going until, like in previous example, you get to something trivial, like just one thing, and you can just return them. And of course, it's a combined step, right? This is the merge the 2 sorted arrays. And I guess somebody already pointed out that this is actually an easy thing to do. Once the arrays are assumed to be sorted, merging them together is a linear operation, right? 2 sorted arrays. Okay, so I'm gonna write down the actual pseudocode for this. So we are actually going to write down pseudocode for the algorithms that we present in this class. I'm going to be a little bit, when I write the algorithms in class, I might actually end up changing some of the notation in the book to look more Pythonic. Probably some of us will be happy about that, some of us may not be, but hopefully that's not going to cause too much confusion. I actually think it's clearer. Okay, so merge sort, I'm going to write down the algorithm, P less than R. Then we have Q equals P plus R on 2. This is finding the midpoint. You're going to call merge sort on A, P, Q. I'll explain what these are in a minute, but I need to just write this down so that it's all there. Q plus 1 R. And I'm going to merge. So this merge is that linear operation I was talking about, P, Q, R, and then I'm going to else return. I guess this is kind of assuming that we're doing it in place, so I'm returning nothing, but I can just return A. Okay, so right, so this thing here sorts the subarray A, P, R. So now I am using Python notation. Maybe I should have put R plus 1 there, but I'll just write A, P, R, right? So this is just the array as a subarray between index P and index R, and so this thing here merges the sorted subarrays A, P, Q, and A, Q plus 1 R. Okay, so we imagine that obviously when we call the function, we're going to be calling A 0 n, right? So the whole thing, but then subsequent calls to the function will require it to act on subarrays, right? So we need to put in these indices and kind of keep track of them. So that's kind of, when I first looked at this, the indices were a little bit confusing, but if you've seen the kind of example and the pseudocode from the, well, this is kind of pseudocode as well, but like the strategy from the previous page, then hopefully this is clear what this is trying to do, right? You're splitting up the array, Q is right in the middle, you decide which way it goes, and then you apply merge sort on APQ, so this is the first bit of the array, then you apply it on the second bit of the array, and then you let them go off and do the thing where it sorts them, and then you apply merge, and then voila, you're done. Okay, so induction has shown that this is, I didn't walk over to the third board. So induction has shown that this is correct. And yes, as Blinky pointed out, this is going to be an induction on the size of the input, not the nth step of the algorithm, because this is really some tree that's executing. recursion leads to a tree, and so there's no nth step, right? Well, there is, depending on which way you go, but we're not doing induction on the nth step. Okay, so the proposition here, I'm going to actually finish off this with a proof. Merge sort is correct. And I guess what this means is that the output array A is sorted in ascending order. Output array is sorted in ascending order. Okay, so the proof here is really is actually quite short. So so we'll do the base case. So the base case cases. Ooh, that was a big eraser. Ascending. Okay, so the base cases, there are two of them. Why did I put brackets? There are actually two base cases. This is crazy. Cases. Okay, so P1, merge sort. Oh, I should actually say, well, we're going to do induction on the size of input array. And the size of the array is just the number of elements that it contains, right? So merge sort is correct on arrays of size 1. Okay, so this is, you go back to the algorithm of size 1, going back there, it doesn't do anything, right? Like for size 1, it was split in the middle. Merge sort will do nothing on the empty list, and for 1, you know, merging an element of size 1 with an empty list will of course give you a the same thing back, and that's by default sorted because there's only one thing in it. So this is trivial, right? This is clear. P2 is slightly less clear, right? That merge sort is correct on arrays of size 2. And the reason why we have to do 1 and 2 is because when we do the induction, we're going to be doing induction as, you know, on arrays of sizes n on 2, and depending on whether it's odd or even, we're going to end up with a base case of 1 or 2, right? So that's why we're doing 1 or 2, 1 and 2 as separate cases. So this requires a little bit of thinking, right? When you feed it through, what happens is that merge sort is called on 2 arrays of size 1, right? Because when you look at the algorithm, right? If you go merge sort with an array of size 2, it gets broken up into, you know, merge sort. Maybe I'll write it like this. This is right. So if you go merge sort of like, you know, A and B, right? What happens is that you're going to get merge sort of A, merge sort B, and right, we already kind of saw before that these are just going to return A back. This is going to give you B back, and then you merge them together, right? When you merge them together, depending on whether A is bigger than B, you're going to get AB or BA, right? So I'll just write, we're going to get AB if A is less than B, and BA if A is greater than or equal to B, right? So whatever happens, the result is going to be in ascending order, right? So on arrays of size 2, this works. And so this is actually most of the argument. The induction case looks very similar to the case we just did, just with more things in it. So the induction step is that we assume merge sort is correct on arrays of size n, of size less than n, right? And then, so when calling merge sort on arrays of size n, what happens is that you got merge sort A. This breaks up into merge sort, I guess, A 0 to n on 2. A n on 2 plus 1, I guess n. Sorry, this is probably not readable. Let me do that again. A n on 2 plus 1 to n. And the point is that these two things are both arrays of size less than n, right? So by induction hypothesis, right, these two are correct, right? The above two steps, or I should say, the above two calls the merge sort, gives you the correct result. Gives correct result. Okay, and so then if we need to merge them together, right? So we do the merge, and finally, right? Finally, I guess merging two sorted arrays is assumed to be correct. So we're done. So yeah, I didn't mention this, right? We're assuming that the merge operation we understand, and that actually always works. Taking two sorted arrays, combining them together will give you, whatever. I didn't actually say how we did it, but we're assuming that there is a merge function that works. And so once you have the induction step of assuming merge sort works on arrays of sizes smaller than n, we're basically done. So you can see this step is actually very similar to the case P2, right? Because there you have you have two elements, you broke them into singleton sets, and then you just combine them together. And so this is, but instead of observing that singleton sets are already sorted, we're using the induction hypothesis to say that, well, the previous step also worked, therefore the next step will also be correct. Okay, so I guess the last thing that I didn't mention is that this obviously terminates because each time you call merge sort, the array size strictly decreases, right? And so eventually, and it will end at 1 and 2, right? 1 or 2, and so the algorithm will terminate. Okay, so I guess that's the last thing I had here. So the other thing I'll say is that going back to the question of how do you get rich, learn the code. Right, that's it.
Yeah. Prove merge sort correct. That's the key.
I actually never did a lot of proving of algorithms being correct when I was taking computer science classes. It's refreshing to kind of say, oh yeah, induction works. Yeah, so I chose this example kind of to, it's not exactly the same as the algorithms. It's not exactly the same as the algorithms that we'll see, but most of us who go through math and see induction, we don't usually apply to algorithms, right? We apply it to like number theoretic statements when we learn this in class. So hopefully this will give you some flavor of how we're going to do this in the course.
Yeah, I think this was a good example. Yeah, thanks, Ken. Are there any questions?